Crazy Math Nerds. It's the big Crazy Math Nerd, Katie Morgan here. And I want to talk to you a little bit about something that's kind of cool. And it's this thing called related rates. We're going to find out why we call it that in just a little bit. But we're going to have to look at how we label things. And there's going to be a lot of written information given to us. So let's look at a few examples of how things are going to look a little different and how we're going to label them. So it says write equations that describe these statements. So if I said John is 5 feet tall, that would be his height. So I would probably say H is 5 feet because that kind of makes sense. You're going to want to label these things, like whatever you're talking about, with variables that make sense to you, okay? If he is growing at a rate, this is a rate because it's inches per year, we're going to call that DH. It's how H is changing. And notice that this is changing in a time period. And so the denominator of this derivative is not X, it's DT, because height is changing with respect to a time unit. And that is going to be 3 inches per year. So notice that the variable at the top should go with your units on the top, as well as this time variable should go with that in your rate. All right? So let's look at B. A storm is 750 miles from shore and is approaching at 200 miles a day. So I would call this distance because the storm is away from you or away from the shore. So I'm going to say D is 750 and it is changing. See how it's approaching? So the distance between the shore and the storm is changing with respect to time because it's per day. And if it is approaching at 200 miles per day, the distance is getting smaller every day. So we say that's a negative 200 miles per day. So notice that John was getting taller, and when he got taller, his rate was positive. If things get smaller, then we say that that's a negative rate. In part C, it says the radius of the puddle is 4 feet. So I'm going to use R because that makes sense to me that I use that. So R is 4 and is not changing, which means dr dt is 0. It is not changing. The radius is not changing. And in part D, the volume of a cone, so V equals 12 pi feet cubed. And in this, guys, anytime you have anything cubed, you're going to be dealing with volume, so be on the lookout for that. And is shrinking, so dV dt, the change of the volume, is shrinking. And when we say when things get smaller, right, or whatever we're talking get smaller, it's going to be a negative 5 pi inches cubed per minute. Okay? So those are the kind of little different things that we're going to be dealing with that are kind of new to you. You hadn't really worked with converting statements into symbols like this. So let's take a look at one of these crazy problems. All right. So it says a 13-foot ladder, probably important, I'm going to underline it, leans against a vertical wall. If the lower end of the ladder is pulled away at a rate of 2 feet per second, so this rate is going to be important. Let me underline that. How fast, here's your question, how fast is the top of the ladder coming down the wall at an instant? Okay? Now, I know there's 2. We're not going to worry about B. I'm just going to do A because it's silly to do both of them. All right, so I need a picture of this. That's the first thing I do when I do a problem like this. And I know that I am dealing with something kind of with respect to time because this rate is 2 feet per second. So notice that it's changing as time changes, okay? So I need to draw a picture of this because I'm visual. I need to see this. So here is my wall. Well, let's make that wall solid. Sorry about that. Here is my wall. Okay, it's still not solid. Thank you very much. Well, that didn't go very well, now did it? Okay, so get me a line. Okay, make it solid. There we go. All right, so there's my, I don't want a red wall. I want a black wall. All right, there's my wall because it's a vertical wall. And so my ladder is going to be, and I'm going to make it dotted because it'll look like a ladder. Ha. My ladder is going to be leaning up against it. So notice that if we actually connect the bottom of the wall to the ladder, we make a fun shape, right? And what kind of shape? Well, of course, that's a triangle. And it's actually a right triangle because the vertical wall would make a 90-degree angle with the ground. All right. So what I'd like to do is I'd like to label the sides of this triangle if that's what I know. And I know the length of the ladder, so I do know that. And this ladder is never going to change. This is not an extendable ladder or anything else. That length is always 13. And we're going to call this distance along the ground from the bottom of the wall to the ladder X. Why? Because we normally call horizontal distances X, and so that's going to make better sense for us to do that. And then we're going to call this vertical distance, you're not going to believe this, oh my gosh, Y. So our job is to write a formula that relates all the things that we know and what we're trying to find together. So now that I've labeled this, let's write down what I do know. I want to know how fast, this is what I want to know, let me highlight that. How fast is the top of the ladder coming down the wall? Well, which variable would that be? That would be the ladder coming down the wall is this Y distance, okay? So if I want to know how fast Y is changing, that's going to be called dy dt because we want to know how the Y distance is changing with respect to time. So that's what we'd like to know. That's our question. And then we're going to draw this long bar here, and that's actually called a WHEN bar, like when. And we're going to put all the things that we know about the problem right here on the when bar, okay? So we know we have a 13-foot ladder, and that's constant. Would y'all like to call this something? Let's call this ladder, L. So we know that L is 13, and it's always 13 because it's not a moving ladder. We know that the end of the ladder is pulled away at a rate of 2 feet per second. Well, this is the end of the ladder, and if it's being pulled away, that means X is changing. So I'm going to write the rate of change of X with respect to time, because that is what this means, rate of 2 feet per second being pulled away from the wall. And what do you notice about X when we pull the ladder away from the wall? It gets bigger. So it's a positive, and I'm just doing this for emphasis, guys, 2 feet per second. Notice that the numerator is feet, and that's what X is measured in, and the denominator is seconds, and that's what my time is being measured in. And so I want to find dy dt when this happens, and I know that I want to find it at a particular instant. And guys, we can only use instantaneous information after we have done something. So when the instant is 12 feet above the ground. So 12 feet above the ground would be Y. So when Y is 12, okay? So if you want to, what we want to do is write an equation that relates X and Y and 13 together because we know something about all of them or their rates, okay? So this is a right triangle, and the sides of a right triangle relate to each other by using the Pythagorean theorem. So I'm going to use the equation that X squared plus Y squared is equal to L squared because that is the Pythagorean theorem. And because L never changes, ever, 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 I can actually write L squared plus Y squared is equal to 13 squared because the ladder length never changes. If it's anything that changes, like I can't put anything in for Y or X because they are varying as the ladder goes down the wall. So now I would like to relate all these rates together, and that means I'm going to take the derivative of each piece. And I'm going to have to do this implicitly because I'm taking the derivative of an x function, but I need to do it with respect to time because I want to know how x changes with respect to time, how y changes with respect to time, and how this constant changes with respect to time. So when I take the derivative, I'm going to do the power rule just like normal, but then I'm going to have to say dx dt because I'm taking the derivative with respect to time, so I must do that implicit differentiation. Okay? And everybody who's not a t, you're going to have to do that chain rule and do that implicit differentiation. So now I'm going to take the derivative of y squared, which is going to be 2y dy dt, and then the derivative of a constant is 0. With respect to x or time, it doesn't matter. All right, once you have done this, once you have implicitly differentiated your equation, notice that this equation relates the rates together. See what I mean? Like all your rates are related together. That's why these are called related rates. And once you do this differentiation, you are then allowed to put all of your instantaneous information in. So now I can put this y is 12 in because it's instantaneously. And so I want to know at this instant what is happening. So let's put in what we know. I don't know x. I know dx dt is 2, so I can put that in. I know that y is 12. And I am actually trying to find dy dt. See, that's my original thing. Well, I want to know what that is, right, when all this is happening. So this is actually good. Ooh, it's actually good that this is left because that's what I'm looking for. Equals 0. So I'm in a little of a quandary because now I have two things I don't know. So sometimes when we get to this point, we have to stop and draw an instantaneous triangle, which is what I'm going to do now. So at the instant when y is 12, this is an instantaneous because at this instant this is happening, I need to know what x is. And I don't know if you know much about Pythagorean triplets, but this is a Pythagorean triplet, and it is the 5, 12, 13 Pythagorean triplet. If you did not know that, you could just put an x there and do x squared plus y squared equals 13, x squared plus 12 squared equals 13 squared and solve that. But knowing this triplet will be very helpful. So I'm going to put in 5 in for my x. And now that makes me only have one thing I don't know, and that is what I'm trying to solve for. So that's good. We like that a lot. Equals 0. And so if you solve for that, you get dy dt equals, all right, before we do this, let's think about it. If this ladder is going down this wall, then what do we know about the distance of y? The distance of y is getting smaller, isn't it, that y height? So if this guy slides out, this guy is sliding down the wall. So I am guessing that dy dt should be negative. And if I don't get a negative answer, then I really need to question myself. So let's see. This is 4 times 5, which is 20, and I'm taking it to the other side, so it's negative. Oh, that's so good. And then 2 times 12 is 24, so I'll be dividing by that. So if you reduce, 4 goes into both of those, you get negative 5, 6. Now I've got to put my units on there. This is dy dt changing, so y is in feet, so that's my unit there, and my time is in seconds. So that is dy dt at the instant when y is 12. And make sure you put your units on there, and they should make sense to how you labeled your problem. Okay? See, this isn't so bad. And so what you're going to end up finding is that we're going to be using like really easy equations that you did back in the day. We're just going to be doing the calculus with them. All right, this question's a little different in the way they wrote it. So let's talk a little bit about this. It says, a rectangle whose sides are changing is 10 and 6. What this is your instantaneous information, like the 12 that we had a minute ago. So this is instantaneous, so kind of know that. I'm kind of going back. They started with this, and I'm kind of going back and looking at it. And so we want to write formulas for both perimeter and area and how fast each is changing. So the perimeter of a rectangle, is it a rectangle? is 2L plus 2W, and the change in the perimeter is going to be dP dt. That's how the perimeter is changing with respect to time. You're going to take the derivative of 2L, 2 is the derivative of 2 variable, right? But then you also have to add the dl dt, so that's that implicit part. Every variable will require a d variable dt, because everything's changing with respect to time. And then for 2w, it's going to be 2 dw dt. For the area of a rectangle is length times width. Notice that length times width is a multiplication which requires the product rule. So when we're asked for the area, the change in area, which is called dA dt, we must do first times the derivative of the second with respect to time, plus second times the derivative of the first with respect to time. Okay? So that's kind of weird. When you have two variables like that, you have to do the product rule. So it's very, very similar to when you did implicit, you had an x and a y, and you had to do the derivative, you had to do the product rule. All right, so now it says, find out how fast each is changing. So it wants to know dP dt and dA dt. Okay, that wants both of those. It says how are they both changing. When, there's your when bar, when the dimensions are 10 and 6, so I guess length is 10 and width is 6. And when the length is decreasing by 4, so that means dl dt is, and it's decreasing, so it's negative 4 inches per second. And then the change in width is increasing, so dw dt, if it's increasing, I'm putting this in for emphasis, the positive 2 inches per second. So we've already really done the work of taking the implicit differentiation. We just have to plug that into these formulas. Let me grab my hand and move that up just a little bit. Okay. So if I were to do this, I've already done the implicit differentiation in the first part. I would do 2 dl dt plus 2 dw dt. And that is negative 8 plus 4, which is negative 4. And this is perimeter, so that is inches per second. I know, I felt Christmas is coming on. Here we go. So I'm changing to red. So if we do the area changing, then dA dt is equal to L, which we're calling 10, times dw dt, which is 2, plus W, which is 6, times dl dt, which is negative 4. And if we do that, we get 20 minus 24, which is negative 4. And this is change in area, so this is going to be inches squared per second, because the change in area would be inches squared, because that's the kind of measurement you have when you do area. That's how area changes. Okay? All right. So the area is getting smaller at this point, at this instant. Okay? All right, so that's just an introduction to this, and when you come back, we'll do part 2 and get into a little bit harder problems, okay? Hope this has helped. Part 2 is on the way.